lesson. We're going to be looking at solving complex trigonometric equations and using technology to do that. Now, a lot of the trig equations that we've looked at so far, they're solvable because they were simple enough that we could use factoring or straightforward algebraic techniques to analyze them. The example that I'm starting with today, x plus sine x equals x cubed, is a little bit more complicated, mostly because we've got an x cubed in it. If I tried some sort of algebraic techniques, I would maybe bring the sine x and the x to the right side, trying to make it equal to 0, but then I would find it very difficult to continue with any kind of algebraic factoring. It just doesn't lend itself. Because it's x cubed, I can't use a quadratic formula, so it's not working. And that's where we need this technology. And by technology, I'm talking about a graphing calculator. Something like this machine. What this allows us to do is choose one of two strategies and use some of the built-in features to find the x's that solve this equation. So I'm going to show you both of these strategies. And every calculator is a little different as far as the makes and models that are out there, so you have to kind of get to know yours. I'm using a Texas Instruments 83 Plus here, but they should all accomplish the same kinds of basic solving techniques. You just got to use the manual that comes with it to make sure. So what I'm going to do in this, to start off, I'm going to use kind of strategy number 1. And what that would be is I'm going to graph the left side and the right side as two separate equations. So I'm going to take the left side and put it in as my first equation. I'm going to hit the y equals button and put in x plus sine x. So that's my first equation. And then I'm going to put the right side in as my second equation. And in how you put x cubed in most calculators would be kind of an up arrow, whoops, it's an up arrow button followed by 3. Sometimes they have built-in cubing buttons as well. So that's what I've done. And the next thing I want to do is I want to have a look at the graph. In order to do that, make sure that under mode that you're set to radians. Unless told otherwise, you should always assume we'd be working in radians. And then the other big thing you have to do before the graph will make any sense is to get a good window setting. That will involve a certain amount of experimentation. And by that I mean you might try a very standard window, which would be -10 to +10, -10 and +10 also in the y direction. That may be not a good enough graph for you, and then you just have to go back to the window setting and try something that refines it and makes it look a little bit better. I'll give you the window settings that I finally found worked pretty well with these two equations, and so I'm going to give you the minimum and maximum x values and something called the scalar. And then I'll also give you the y minimums and maximums, as well as the y scalar. So, if I have a look at the settings that I used here, I found that a -2 as an x minimum, and a +2 as a maximum, and a scalar of 1 seemed to work pretty well. And over here I used -5 to +5, also with a scalar of 1. So what we end up doing is we graph it and we go, well, that looks pretty reasonable. We get a pretty reasonable looking picture. And then how do we solve this picture? Well, I'll just put the steps up here. Because I've graphed the left and the right side of the original equation as two separate equations, what I'm looking for is where does this equal this? and that's known as the points of intersection. So on this particular calculator, I would use some built-in functions called second function trace. Those are the particular buttons that I would be pressing here. And what I'm after is intersect. Now, a different calculator will probably have a different way to get to finding the intersection of the two graphs, and you'll just have to check the manual on that. Once I choose intersect, I just position the cursor basically over top one of the intersection points, and I can see that there are 3 intersection points where the two graphs are crossing. And then I hit, it says first curve, I'm just going to hit enter, 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 and then that gives us our intersection. And so one of the solutions here is an x value of negative 1.32. I'll just round that. You'll notice I'm not interested in the y value at all. Why is that? Well, in the original equation, there is no y. So I'm really only after the x's in this case. So now I have 2 more solutions to find, and I just repeat the process of second function trace. I choose intersect, and I position the cursor over top. This time what seems to be the second intersection point. Looks a little bit like 0, 0. Well, let's find out. Enter, 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 and we've got 0, 0. So an x value of 0 is correct. And then one more time. Positioning the cursor over top of the intersection of the two graphs, the last point there on the right, and enter, 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 and I get positive 1.32. And so I have solved this original equation through technology. So this was one strategy, where we graph the left side and the right side as 2 separate equations. Let me show you a second strategy that will accomplish the same thing. For the second strategy, I'm going to do it with only one equation. So this is strategy number 2. I'm going to do a little bit of algebra here. I'm going to move x cubed to the left side. So it looks like this. X plus sine x minus x cubed equals 0. The key to this strategy is that I've made it equal 0. So I'm now going to graph this left side. So I go y equals and put in the entire left side. And then I go ahead and graph. So let's have a little look here. So I'm going to type in x plus sine x minus x cubed and hit graph. Now I'm just looking at one graph, and it's typically a little cubic graph, of course, dominated being a third-degree equation. And because I'm only looking at one graph, I'm not looking for an intersection this time. However, I'm still going to go to second function trace. And this time, what I'm looking for is when does this equal 0? When, for what x's is the y 0? And of course, we call those points zeros. So I choose 0. And on the graph, it means I have to go through a little procedure here. So I've chosen 0. On this particular calculator, what's involved is, it says left boundary. And what that means is, I'll just give you an idea here what the graph kind of looks like. What I have is essentially this. Now I'm going to try and find this point here. I'm going to find that 0. Now in order to accommodate that, on the calculator I have to go to what's called the left boundary. So I'm moving the cursor to the left side. Here's where the 0, I believe, is. And so that's the x value I'm after. On the left side of that means I'm going to position the cursor up there somewhere. So I do that and I hit enter. And then it says right boundary, so I have to move the cursor somewhere to the right of where that 0 is. So I do that. And then it says guess, but we won't bother. We'll just hit enter one more time. And of course, surprisingly, we get exactly this number here. Negative 1.32. Same solution. Of course, the only difference is this time it has a different y value, but yet again, we don't care about the y value. Okay? Now, I would repeat that process to find that 0 and that 0, but I can tell you you're going to get the same 3 solutions we got using the other strategy. So, technology is there, and it's very helpful when it comes to equations which we would not be able to solve using traditional algebraic techniques. And that's about all there is to it. Enjoy working with your graphing calculator. We'll catch you later.